Just for this last note, we're going to just do a little bit of an introduction and something that's going to be covered a lot more thoroughly later. What we are basically looking at here is a bit of equation solving, how to really properly undo these trig ratios. None of the trig functions, sine, cos, or tan, are actually one-to-one. So when we try equation solving, we use those inverse functions, but it's kind of like using a square root to solve an equation. Like if you're solving, for example, x squared equals 4, we don't just use a square root to get x is root 4 equals 2. We're missing a solution when we do that. We actually have to throw a plus minus on there to actually get the full set of solutions. And with trig, the problem is actually even a little bit worse. So we have to be a bit mindful of the fact that these are not one-to-one functions. We are going to hit problems. Yeah, so to tackle something like this, we want sine theta is -1/2. So one thing that we could do is actually look at this from an opposite adjacent hypotenuse perspective. So we could say that that means that the opposite is -1 and the hypotenuse is 2. And so what we'll do is draw how this can possibly happen. Now, it might also be worth noting, if the opposite is -1, this is the same as saying that in our XYR, y is -1 and r is 2. R does have to be positive, so that means that we can't like flip around the -1 and make it like 1/-2. It has to go on the y, that -1. So we're going to draw where this can happen. Well, if y equals -1, that means it has to be below the x-axis. So quadrant 3 and quadrant 4. So what we'll do is draw those. You know what's going to happen along the bottom. My triangles always follow a really particular pattern in that they're always going to use the x-axis. So if I make my way across, I'll use the x-axis. So I don't care totally what the x is, but what I do need is that y goes down. And so I could have a triangle like that, and I could label this thing as -1 and 2. And I could also have it in quadrant 3. There's nothing stopping me from being on this side as well. So again, I'll use my x-axis and then go down. And I'm actually fairly intentionally not drawing this with any kind of scale in mind. And again, -1 and 2 for my sides there. And now if I look at this picture, I don't necessarily need to find the third side, but what I do need to do is figure out what the reference angle is going to be. And what I can do now is look at those sides of the 2 and the -1, and you'll notice that if you have 2 and 1, we actually are going to get this special triangle with the hypotenuse of 2 and a side of 1. The other side would be √3. -√3 on the left. It doesn't totally matter, but that tells me what my reference angle is. It's the angle squeezed between the 2 and the √3. It would be 30 degrees for those reference angles. So that tells me at least a little bit more information. And now if I want to actually find the angles where this happened, I can see that there's 2 answers right from this picture. So the first answer, which I'll do in orange, we always start at the positive x-axis and then make our way to the terminal side, which is the hypotenuse. And so if we go around like this, the first answer, I'll call it maybe θ1, is going to be 180 plus 30 degrees, so 210 degrees. And my second answer is gonna, well, I could actually just go left. Why not? And since it's counterclockwise, it would be, say, negative 30 degrees. But you might have noticed I also could have gone to the right. So I also could have gone a full 360 and then back another 30 to get 330 degrees. I could have also just done completely arbitrary loops. I could do as many circles around as I want. I could add that. The reality is I can add as many full complete circles as I want, and I end up at the exact same terminal sides, and all the ratios are based off the terminal sides. So what we could also do is add any multiple of 360 degrees. So you could express that by just writing like k times 360 degrees, and we could also do that for the other solution here. So again, we'll talk more about this later on when we get into a bit more about equation solving, but it's nice to actually see a bit of an action before you really get your hands dirty with it later. So hopefully it sinks in a little bit better. I think this will probably come up, I think, in next week's topic more thoroughly. So, but yeah, the key takeaway that I want from this, though, is that it's not one-to-one. Sine, cosine, tangent are not one-to-one. That means it's going to be a lot of really annoying things that we have to do when we solve equations, and it involves going backwards of these drawings that we've already started drawing. So you have to at least be a little bit handy with these illustrations.